Okay, so today we'll start with dynamics review. Dynamics is the part of physics that deals with as the biggest question, why the object is moving the way that it is moving. So we said in kinematics that the object is moving in a uniform motion or in a non-uniform motion. And we talked about how to see and on kinematics we analyze the motion and how the object is moving in terms of what is the acceleration, what is the acceleration, what is one second. Let's continue with the review dynamics. So we said in kinematics that there are two types of motions, uniform and non-uniform motion, and then we had a bunch of ways to analyze the motion. One was using kinematics equation, then it was graphing, and then we went even on the different specific motions like relative motion or the projectile. Now dynamics deal with a question, why is the object moving, let's say, in uniform motion or non-uniform motion? As we have mentioned, the person, the scientist that was dealing with the physics that's kind of put the foot into the physics as we know now is Newton. And Newton was saying that the reason that the object is moving in the way that is moving is because of the forces that he is experiencing, all the forces that he's experiencing. So now we have a new concept of that is the concept of force. Force is a vector quantity. We know now that force is a vector quantity. And as a vector quantity, in order to fully describe it, we have to define magnitude and direction, like any vector that we have talked prior to this. Now, when we analyze forces, then we notice that forces are at two types. The first one is forces that are experienced when you are in contact with the object, and the forces that are at a distance. Forces that are at a contact with an object are forces like force applied, force of friction, force normal, and forces that are at a distance, the one that we will see and study more on Physics 20 is that is known as the force of gravity. But then any force that is experienced even though that the objects are not in contact with each other, they are known as forces at a distance. When you move to Physics 30, you will see that even electric force and magnetic forces are forces at a distance. Those forces at a distance exist when there is that is known as the field that is surrounding the object. So since we are here, let's discuss about the field concept, which actually is part of the second uniform gravity. But now that we are doing a review, it kind of makes sense to do. Okay, so when we have an object that has a mass, any object that has a mass, what is happening? This object is surrounding by an area in which if you place another object on this area, then we will see an interaction. So this is the concept of the field in general. If that being a gravity field or electric field or or magnetic field. If you have an object that is like the source that has a mass in our case and is surrounded by a field. This field is known as the gravitational field for the terms of mass. And when you see the charges, then it is known as the electric field. And when you see a magnet, then it's known as the magnetic field. So now, the field is identified, the configuration of the field is identified by placing a test object on the area. So the test object on this case, when we have an object with a mass, so in the case of the gravity, will be an object that the mass of it is way smaller than the mass of the source. So it is not important what is the mass of the source and what is the mass of the test object, but it is important to see that the relationship between the test mass and the source mass are in mass of the test is way smaller than mass of the source. And as we put the object in the area where the field exists, then we will see the interaction. And in this case, when we put the object here, what do we see is that the test is attracted to the center of the mass. And then we put somewhere in here, and the test is attracted to the center of the source. And this will be the configuration of the field. As you see here, the configuration of gravitational field in this case as you see, the gravitational field, like any field, is a vector quantity. So the way that we measure the field is by that is known as the field strength. In our case, the field strength is a vector quantity that is known with a lowercase g. And now we know even from kinematics that near the surface of the Earth, g is 9.81. But as you move away from the surface of the Earth, what is happening with the gravitational field strength? It is becoming smaller and smaller. And the relationship mathematically between the gravitational field strength and the distance is capital G, mass of the source, over r squared, where capital G is the universal constant 6.6667 times 10 to the power of -11. Mass of the source is whatever is the mass of the source in kilogram, and r squared is r is the distance from the center of the source to the point that you are measuring the gravitational field strength. Now, the relationship between the gravitational field strength and the distance, the magnitude of the gravitational field strength and the distance is something like this, where this one here is the radius of the source, this distance here. And this is continuing, having the horizontal axis as the asymptote, meaning that will approach infinitely but not intersect it. Now, force of gravity, on the other hand, is interaction or the force interaction between the source and the other object, and maybe a test object or maybe another object. Force of gravity is calculated as capital G mass 1 mass 2 over r squared, where capital G is the universal force of gravity or universal constant. Mass 1 is mass of one object, mass 2 is mass of the other object, and r squared is the r is the distance between the center of the mass and the center of the object. Even from what we see here, the relationship between force of gravity and the distance is an inverse squared, so it is like this. And in order to straighten it, what do we have to do? We have to manipulate the horizontal axis, make it as 1 over r squared, so that the graph then will be magnitude of it. The graph will be a straight line, and the slope of the graph will be the product of universal constant, gravity constant, and mass 1, mass 2. From here, as soon as we know what the slope is, we can find either the gravity or the product of the two masses. Now, when we are talking about forces, the way to identify what forces the object is experiencing, we have to build a that is known as the free body diagram. A free body diagram, the word is saying it, it is a diagram that is free of the object. So if we have as a situational diagram an object that is with a given mass, let's say mass is 10 kilograms, that is in a horizontal surface with or without force applied, let's say that is without. This diagram that we represent here is known as the situational diagram. So it is a diagram that is telling us what the situation is. This is pretty much what you will see in real life. You will see a horizontal surface and an object with a certain shape, and in this case is like a box on this object. The free body diagram, on the other hand, is a diagram that is free of the object. So the object of our interest is the object with mass 10 kilograms. So this object is represented by a dot. This dot, you will learn it in a higher level of physics, is actually the center of mass of the object, and it is calculated with high calculus, high mathematical calculations. It is a dot that all the mass of the object is concentrated on that point. So we'll start with that is the universal force. And the universal force is the universal force of gravity, which is a force that starts from the object and goes toward the center of the earth. The universal force of gravity, since we are dealing with a force that is near the surface of the earth, will be equal to mass of the object times acceleration due to gravity at near the surface of the earth, so that we said is a constant value, is accepted to be a constant value as 9.81. So this will be 10 times 9.81, and it is 98.1 newtons. And then since the object is on a surface and the surface is horizontal, then we will have another force that is force at the contact, and it is a force normal. Force normal is a force that is always perpendicular or 90 degrees with the surface. No matter what the surface is horizontal, then force normal will be perpendicular to horizontal. The surface is an incline, and you have an object here, then force of gravity will be always going down to the center of the Earth, and force normal will be always perpendicular to the surface of the Earth. And this, to the surface that the object is supported on. And this is always true. Now, another force that we talk a lot on dynamics is that is known as the force of friction. Force of friction is a force that is always opposing the motion. So in the case when we have a horizontal surface like this, and let's suppose that we have a force applied that is here, then force of friction will exist between the object and the surface. And since we are assuming that the direction of the motion is going east, let's say, then force of friction will be against the motion. So if on this case, on the incline case, we are assuming that the object will fall down the incline, then force of friction will be against the motion. It's always against the motion. Another force that we use a lot on terms of the, and this will look in the free body diagram, will look something like this, or in the incline will look something like this. Another force that we discuss a lot in dynamics is that is known as the tension force. And the tension force exists when the object is tied with string. And the assumption that we are doing here is that the string doesn't have any elasticity. So that means that the tension on each section of the string is the same in magnitude. And if the string changes the direction, in the case of the pulley, the magnitude will be the same, even though that the direction is not. So the magnitude of the string will be the same. And the definition, or the way that we approach the tension, is that we say that the tension starts from the object and goes along the string. So in the case when we have an object that is hanged with two strings, string 1 and string 2, at a certain angle, let's say angle 30 and 40 degrees with the horizontal line, and then here we have an object with weight now, which is the same as the force of gravity, with weight, let's say 200 newtons. And what we are doing is we are identifying what is the tension on string 1 and string 2. This, being the situational diagram, will be translated into the free body diagram, where the object of our interest, that is the object with weight 200 newtons, is represented by a dot. And now the weight is a vector quantity, and it is equal to the force of gravity. And then for the tension, so we will say starting from the object going along the string. So this will be tension 2. And starting from the object going along the string, and this will be tension 1. The angle with the horizontal for both of those will be respectively 30 for tension 1 and 40 for tension 2. Now, since in this case the object is in equilibrium, then, first of all, there is no force normal here because the object is not on the surface, and there is no force of friction because the object is not moving. So what is happening with the object is in equilibrium. Being in equilibrium means that the sum of all the forces that the object is experiencing is equal to 0. This is what we will use to solve for T1 and T2 here. Now, even if we have a pulley, so let's say that we have a pulley here with two masses that are hanged into two different, and for simplicity, I will do weight 1 is 150 newtons and weight 2 is 250 newtons. Then when we are drawing the free body diagram for each of those objects, so we'll go for object 1, we will have weight 1 as 150 newtons, and here we will have tension. And for object 2, we will have weight 2 is 250 newtons, and tension is this one here. Notice here that the tension is not T1 and T2 because we have one string that is going around the pulley, and this will make the tension equal on each section of the string. And on some cases, when one of the masses, let's say it's on an incline, the direction of the tension may change, but the magnitude of the tension will not change. And then since we are drawing the free body diagram, we don't have to state what is the direction of tension 1 or tension 2, because we know the direction based on the free body diagram. Even on this case, we do not have force of friction or force normal because the object is not on a surface. The way that we solve it is we state the direction of the motion, and then we say object 1 is moving up, object 2 is moving down. So then based on this, we built the table of components. Now, when we are analyzing forces, we may have even a force applied. Okay, so as long as the string is the same, so it's the same, you will have the same tension. So this is a same string. You will have the same tension. This is the same string. You will have the same tension. This is the same string. You will have the same tension. And this is the same string, and you will have the same tension. And the free body diagram for each of those situations will be something like this. And you will do the table of components and then equal it to mass times mass 1, mass 2, mass 3 for each of the objects times acceleration. Now the acceleration is the same here because it is the acceleration of the system. Now if we have, in order to manage the y, we have to establish some rules. And those rules are known as the 3 laws of Newton, or laws of motion, or Newton's law. The first one is known as the law of inertia. So it's saying that the object will stay at the state that is at for as long as the forces stays the same. So if the object is at rest, it will stay at rest until as long as the forces stay the same, until no other forces is interacting into the object. The object will keep moving at a constant acceleration for as long as all the forces or no other forces are acting into the object. So this is known as the inertia law. The second law is known as the force net. So force net is equal to mass times acceleration. This is what it's saying. And what force net is the sum of all the forces that the object is experiencing. How do we do this? How do we find this? Using the free body diagram. This is why we build the free body diagram to figure out what are the forces that the object is experiencing. And based on this, so we say that, okay, if it is an unbalanced force, then it is equal to mass times acceleration. And force net is actually the sum of all the forces. It's the same as the resultant vector that we have said and discussed at unit 0. The third law is known as the action-reaction law. So if we have two objects that are interacting between each other, let's say two object force of gravity, then the force that object 1 is experiencing as a result of object 2 is equal in magnitude but opposite direction as the force that object 2 is exerting to object 1. Those two forces, even though that are opposite direction with the same magnitude, which if they are on the same object, they will cancel out each other, do not cancel out because there are forces that are experiencing in two different objects. So this is the force that object 1 is experiencing as a result of the presence or contact with object 2, and this is the force that object 2 is experiencing as a result of the presence or contact with object 1. So they do not cancel out because they are experiencing two different objects. Now, the typical questions that we have in dynamics are the one that are known as the equilibrium questions. And what it is an object with a given mass or weight is tied with two strings. So let's say weight 100 newtons. And then we have tension or string 1 and string 2 that are creating an angle of 32 degrees with the horizontal and 43 degrees. So now, in order to solve this, what do we have to assume here is that the strings do not have any elasticity, and as a result of this, the tension on the string, since it is a continuous string, will be the same at every session of it, either this being tension 1 or being tension 2. So now let's convert this into a free body diagram because this is a situational diagram. So what we will see is the weight here as 100 newtons, and then here we will have tension 2, and here we will have tension 1, creating with the horizontal respectively 32 and 43 degrees angle. Now, since it is in equilibrium, then what we have here is that the sum of all the forces that the object is experiencing is equal to 0. It's not moving. Even if we apply the first law or the second law of motion, we still will have that acceleration is 0, the object is at rest, so therefore we have force net equal to 0. Then what we do is we build the table of components. So we start with force of gravity or weight is the same thing, and then we go tension 1, tension 2, and after we are done with all the forces that the object is experiencing, then we write force net. So horizontal component of force of gravity is equal to 0, vertical component is negative 100. The horizontal component of tension 1 is negative, as you see it here, is a negative T1 times cosine 32 degrees, and the vertical component is this one here. So it is positive, will be positive T1 times sine 32 degrees. And if we move to T2, then we will see that T2 horizontal component is in this direction, so it's positive T2 times cosine 43 degrees. And vertical component is again positive T2 vertical, and will be positive T2 times sine 43 degrees. And as we said, force net is equal to 0. From here, we build the table of component to construct two equations. So from here, we have the horizontal is telling us that negative T1 cosine 32 plus T2 cosine 43 is equal to 0. And the vertical component is telling us that T1 sine 32 plus T2 cosine 43 degrees is equal to 100. We can solve this any way we want. You can solve it using math, substitution, yeah, substitution is the one that you should go, or you can solve it using your calculator, the way that I have told you to do when we were working on equilibrium questions. Do you have any questions? The second type of questions that we deal with in kinematics is those that are known as pulleys. And what we do is we have a pulley that we are assuming that it's no friction when the string passes through it. And then we have two objects with mass or weight, whatever the question is telling us. And what we are looking for is what is the acceleration of the object or of the system, and what is the tension on the string. As we said even before, since it is one string that is going around the pulley, then the tension will be the same. So then this being the situational diagram, the free body diagram for each of those objects will be something like this. For the first one, we'll have force of gravity 1 and tension 1, and tension, not tension 1, tension. And for the second object, we will have force of gravity 2 and tension. Okay, now if we put some numbers here, let's say that weight 1 is equal to 15 newtons and weight 2 is equal to 30 newtons. So then based on this, we choose a direction in which the system is moving. And since weight 1 is greater than weight 2, we naturally choose counterclockwise. But even if you choose not like clockwise, if you choose the wrong direction, when there is no friction, there is nothing wrong with it. So in this case, the proper direction in which the system is moving is counterclockwise. But even if you choose the other one, if you choose the clockwise one, what you will have based on the calculation, since there is no friction here, you will see that the acceleration will be negative, and the only thing that you have to say is that the direction is the opposite. So in this case, what we have, object 1 is going down and object 2 is moving up. So this is positive and this is positive. And then based on this, or the direction of the motion, let's say not positive. So this is the direction of motion. So then based on this, what do? Is we built again the table of components, horizontal, vertical, force of gravity 1, tension, and force net. And then what do we have here for the horizontal is 0, 0, 0. For what do we have for the vertical is a negative 50 and tension is positive. And now what do we have is that the object is going down, so it will be negative mass 1 times acceleration. How do we find mass 1? Mass 1 is found by using the fact that we have a weight 1 as 50, and this is as a result of the product of mass and acceleration due to gravity near the surface of the Earth. So this will be 50 newtons over 9.81 meters per second squared. And mass 2 is the same thing, weight 2 over g as 30 newtons over 9.81 meters per second squared. So that means that, we'll talk about units in a bit. So this is for object 1, and for object 2, what do we have is pretty much the same thing, force of gravity 2, tension, and force net. So 0, 0, 0 for the horizontal, and for the vertical is negative 30, and this will be positive tension, and this will be positive mass 2 times acceleration. So now from here we will have two equations from the verticals, this one and this one, with two variables, tension and acceleration, and this is what we will find. You can solve it using anything, using either math or using the calculator. At this point, it doesn't really matter. You can do whatever you want. Questions? The third type of questions that we see is that is known as the inclined plane. What is unique on this is what we are doing. Actually, we are rotating the axis. So if we have an incline that is creating a certain angle with the horizontal, this being the situational diagram, and we have an object with mass, so let's say 15 kilograms, and the incline is creating an angle of 30 degrees with the horizontal. This being the situational diagram, converted into free body diagram, will be the object of our interest, which is the object with mass 15, is represented by a dot. Then we have force of gravity, and then we have a surface that is creating an angle of 30 degrees with the horizontal, and perpendicular to the surface, we will have force normal. Now, if we are keeping the axis the way that we are used to in math, having the horizontal and vertical like this, will be a lot of work. However, if we rotate the axis and make it the horizontal is on the direction of the motion, and the vertical is perpendicular to the surface, then the work is way easier. What we do is we extend the vertical axis, and then the angle that is created between the extension of the vertical axis and the force of gravity is the same as the angle of the incline. And on this way, what we have is we have two components, the vertical component of force of gravity, the rotated one now, and the horizontal component of force of gravity, but they're rotated now. So in this way, what we do is we build the table of component, but now not with a horizontal, but with the rotated horizontal and the rotated vertical. So we will have force of gravity and force normal. And since there is no other forces, if there is force of friction, then we will draw the force of friction opposite to the direction of the motion. of motion. If there is any force applied, then we will put it the way that it is. In this case, there is nothing, so will be force net. So horizontal force of gravity in the new rotated axis will be positive. It's positive because it is on the same direction as the new horizontal axis, and will be whatever is mass of the object times acceleration times sine 30 degrees. And the vertical component of force of gravity will be negative because it is in the opposite direction of the positive vertical axis, and will be mass of the object times acceleration due to gravity times cosine 30. Make sure that the mode of your calculator is on degrees. This is especially with students that are taking math at the same time. 30, they forget to change the mode of the calculator when they are in physics into degrees only. The horizontal component of force of normal is 0, and the vertical component is positive force normal. In the horizontal axis, this is where the object is moving, and then we will have positive mass times acceleration. And on the vertical axis, the object is not moving. From the vertical axis, we find what is. From the vertical axis, we find what is force normal. So force normal is equal to mass G cosine 30 degrees. And from the horizontal, what do we find is mg sine 30 is equal to m times a. Mass is the same, so acceleration will be g times sine 30 degrees, which is sine of the angle of the incline. And if this is a common, like a general one, theta, then acceleration will be g times sine theta. Now, the combination of an incline, either horizontal, straight horizontal, and a pulley, you may see. So this is like a combinational. So if we have a horizontal surface, and then at the corner of it, we will have a pulley. And then here we will have two objects. Let's say mass 1 is equal to 10 kilograms, and mass 2 is equal to 15 kilograms. And now what we have here is a coefficient of the friction 0.15. And when you see the coefficient of the friction is the ratio between force normal and force of gravity. So now what it is always less than 1. So coefficient of the friction is always less than 1 or equal or greater than 0. It is in this interval. Even in the questions, if you see something like what is the coefficient of the friction, and one of the option is 1 point something, then that option is eliminated right away. So it doesn't exist. Now, when we are building the free body diagram of each of those objects, we'll start with object 1. First of all, the direction of the motion will be this one here. We state the direction of the motion at the situational diagram, and even if there is no situational diagram given in a question, you can draw a situational diagram based on the information that you have on the English part of the question. So for object 1, the free body diagram will be something like this. Force of gravity 1, that will be 98.1 newtons, and for a tension. Now again, since we have one string that starts at object 1, goes around the pulley and moves to object 2, then tension is the same. And for object 2, the free body diagram will be a bit more complicated because we will have force of gravity, which is 15 times 9.81, will be 147.15 newtons. And then since it is on the surface, then we will have force normal as perpendicular to the surface. We will have a tension that is from the object along the string, and we will have a force of friction. Now this object is moving, object 1 is moving down, and object 2 is moving to the right. Now, based on this free body diagram, we built the table of components. For object 1, we will have horizontal and vertical, force of gravity 1, tension, and force net. Then on the horizontal, everything is equal to 0. On the vertical, what we have is negative 98.1. Positive tension, mass 1, positive, negative. This is negative, mass 1 times acceleration. So it will be negative 10 times acceleration. From this, we have the first equation. Let's move now to the second table of component for the second object. So we'll have horizontal and vertical. We'll have force of gravity 2, tension, force normal. You can say force normal 2, it's fine. Force of friction, and then force net. So force of gravity 2 in the horizontal will be equals to 0, and the vertical will be negative 147.15. Tension in the horizontal, see now what it is? Tension in the horizontal is positive tension, and on the vertical is equal to 0. Force normal in the horizontal is 0, in the vertical is positive force normal. Force of friction in the horizontal is negative force of friction, and in the vertical is 0. Now the object is moving in the horizontal direction, so it will be positive m2 times acceleration, or positive mass 2 was 15 times acceleration, and it's not moving in the vertical, and then we have equals to 0. So in this case, we will use both the horizontal and the vertical relations. So let's write all the equations that we have here. From object 1 horizontal, we have negative 98.1 plus tension is equal to negative 10 times acceleration. From the horizontal of object 2, what we have is tension minus force of friction is equal to positive 15 times acceleration. And from the vertical of object 2, what we have is negative 147.15 plus force normal is equal to 0. So now we have 3 equations with 3 variables, 1, 2, 3, and the variables are F net, force, 4 variables, F net, force, friction, tension, and acceleration. Let's start solving it starting with the easiest one. So the easiest one to solve, or when I say the easiest one, is the equation with 1 variable on it. So force normal is equal to 147.15 newtons. Using the fact that force of friction is equal to force in magnitude mu, coefficient of the friction, times force normal, then this will be 0.15 times 147.15. So times 0.15 will be equals to 22.07 newtons. So force of friction will be 22.07 newtons. we can substitute this value in the equation that we get from the horizontal of object 2. And then what it is now turned out, all this system is turned out to be into negative 98.1 plus tension is equal to negative 10 times acceleration, and the tension minus 22.07 is equal to 15 times acceleration. And again, you can solve it any way you want. You can solve it using calculator or not, whatever you want, or elimination or substitution. On this case, both will be the same. The way that you solve it doesn't really matter. What it is important is that you have the correct values. Question? Now, when you have an incline and a pulley, let's say you have a pulley here. Again, the problem will be the same. You will have to draw the situational diagram, and you have to draw the free body diagram. So based on the situational diagram, you will draw the free body diagram. So let's say that this is 0.15, and here you have a 30 degree again. Then the free body diagram for object 1 will be force of gravity that is always going down. Then you will have, since it is on an incline, you will have force normal. And you will have, let's assume that the direction of the motion is this one. Of motion. So then opposing the direction of the motion, you will have force of friction that is this way. And you will have the tension going from the object along the string. And then what you will do is you again will break this into two components, a horizontal component and a vertical component. This being the vertical component of the new rotated one, and this being the horizontal component of the new rotated axis. Now, axes are, again, we will say the same thing, are along the direction of the motion and perpendicular to it. This will be the new axis. So the horizontal component of force of gravity will be negative because it is in the opposite direction. Tension will be positive. Force of friction will be negative. The vertical again is negative. And when we are drawing the free body diagram for object 2, it's easier because what we will do is we will have force of gravity 2 and tension 2. Tension is the same tension. Now the acceleration is the same again. We will do all the work as we have done in the incline with the same logic, building the table of components and then starting to solve it slowly, starting with the equation that gives us the force normal. And then from there, we solve the force of friction, and then we move to acceleration and tension. I will come